Good afternoon. This is Dr. Heidelberg, and this presentation will discuss Module 2, robot types. So we will use the PowerPoint presentation in Module 2. We'll click on Module 2 in a Blackboard. And we have over here reference material, lecture notes. This is robot types. This is a PDF. We click on that and we come into the presentation. So what we will do here is we will cover the basic topics on this presentation, and you will follow up the details as part of your homework assignment. We will discuss robot block diagram, some basic definitions, types and construction of robots, robot performance specifications, and relationship between system analysis and experimental testing that we will be doing in the lab. This is a typical diagram that shows most of the components related to automation process. We see over here an example of a process where there is a carousel, there are conveyor belts that bring in parts, there are robots that handle the parts from one station to the other, place them from the conveyor to the carousel, or take them from the carousel into some process machine. We see equipment which are so-called hoppers that feed in equipment. All of these are so-called peripheral equipment that work together in tandem with the robots to manufacture parts. We see over here an example of a conveyor belt. We see over here a machining center. The process starts with the higher level controller, which is related to so-called Industry 4, Internet of Things. So this particular controller is connected to the entire enterprise systems with a lot more sensors and information and databases which are fed in to this controller in order to help controlling this entire process that we will be focusing on. The process is controlled by a device which is called PLC, Programmable Logic Controller. And the Programmable Logic Controller is connected to all the peripheral equipment, as we see over here, through the Ethernet typically, and it basically orchestrates the process one at a time of each one of these components. So a conveyor belt may be commanded to move until the sensor feeds back that the box has reached the sensor, and then the PLC will command the robot to pick up the box and place it in a machining center. Then the robot will command back to the PLC that it's done its process, and the PLC will command the machining center to start its process, and so on. The PLC is commanded by a human operator, could be a programmable operator, a maintenance person, assembler, tester. It could be used a laptop or PC or a teaching pendant. And all these instructions are coming into the PLC, they are stored there, and then the PLC uses them in order to obtain, with the input and output modules, the feedback from the peripheral and the commands to the peripheral. The PLC in turn commands also the robot motion controller. Each robot has several degrees of freedom which it can move with. Like, for example, we see over here an articulating robot that has several links in it, and over here is the tool center point with where the gripper picks up the part, or the tool is processing the part, and each one of these degrees of freedom is being controlled by a servo amplifier. So typically we have 6 degrees of freedom, 3 which are linear, 3 which are rotary, and the robot motion controller is controlling all 6 of them in sync, such that they will be moving together in a prescribed path of motion. The PLC commands the robot to move, and the robot motion controller, with its software, which is embedded in it, will command each one of these servo amplifiers to do its motion. Now, the servo amplifier of each degree of freedom is providing high power to the motor, which drives the actuator, specific actuator. Each one of these links could be viewed as an actuator, and each actuator has a limit switch to determine the limits of its travel of motion, and it also has an encoder which feeds back the position of that link back to the motion controller. The motion controller checks the actual position, which was written in the software, with the desired position, which was written with the software, with the actual position, which is fed back by the encoder, and then the result is a function of the error and the derivative of the error, or the integral of the error, or so-called PID, which goes back to the servo amplifier to make a correction in the link position or the actuator position in order to achieve the desired position. The communication between the robot motion controller and each one of these servo amplifiers is done through a field bus, and the power is provided from the power supply through a power bus to each one of these servo amplifiers. This basically includes most of the components. We may want also to mention that there's a human-machine interface, HMI, which could be also connected to the motion controller, such as touch buttons. That the most important one is the emergency is off, emergency button off, and then this basically means that if the operator pushes in the EMO button, then the whole machine process will stop. Some of the common terms used are pulse width modulation. It's the way that the servo amplifier feeds in currents, high power currents, into the motor. The power supply over here is the device that provides the power to the servo amplifier. HMI, human machine interface, emergency machine off is the EMO, and IoT is the Internet of Things. We will not go over the basic definitions, but this is something that you could review. Some definitions of Internet of Things in manufacturing, definition of distributed manufacturing, and basic definitions of field bus. Here's an example, a typical example of a distributed process motion system, where here is a control logics of Rockwell Automation, where we see the power supply, the PLC, and various modules over here for the servo amplifier and input-output. Another common PLC system, which is Simatics PCS7 of Siemens. You see over here is a human-machine interface, and you see over here the PLC, the power supply, and the connection to the network, which commands all these peripheral equipments which are part of the automation system. We have also a common definition of a manufacturing cell, which is a group of automation equipment which are operating together. We see over here an example of a robot which receives parts from one conveyor, feeds it into a machine over here, a lathe, and then it receives parts from a second conveyor, and then or a pallet, and it feeds in another lathe. Once the parts are finished their process in the lathe, the robot will pick the finished parts and put it over here in a milling machine, and when the process in the milling machine is finished, then the robot will put it on the output pallet. The whole process is commanded by the PLC, and in order to visualize the time that the process will take from the time that the robot picks it up on a pallet or on a conveyor until it's being placed on an output pallet, then we need to work with a time and motion diagram. And this is an example where we, over here on the first column, list all the different equipment, lathe 1, lathe 2, milling, and part on a pallet. And then over here we have the time. Each one of these elements could represent a certain time element, like a second. We have the definition of each one of these equipment, how long it takes for it to process. Like, for example, loading the part from pallet 1 to lathe takes 5 seconds. Loading the part from lathe to the milling machine takes 3 seconds. And peripheral machine process time, each one of these lathe takes 10 seconds to process. So you see that over here we could start by looking at the robot picking up the first part from the first pallet, okay, and we define this by Li, comma J, part J, which is processed on lathe number I. So this is lathe 1 of part 1. So we take part 1 with the robot. It takes 5 minutes to load it to the lathe, and then the lathe starts to work on it over here, L11, for 10 seconds. Meanwhile, the robot is picking up the second part, the first part from pallet 1 going to lathe 2, so L21, and it feeds it to the second lathe, and then you see that in green the 10 seconds for each process time is being counted, and then the robot has some latent time that it doesn't have anything to do because the two parts are being still in process. And then after the 10 minutes over here is done, then the robot picks up the part over here, and it within 3 seconds it puts it in the milling machine, and then the milling machine starts its process, and then so on and so forth. Now when we finish this whole process, we notice that the startup takes longer than the steady state. Once everything is done and settled, the steady state throughput is 22 seconds, and that is the time that it takes for a part to be picked by the robot and be placed on the output by the robot. But to start with, which happens once a shift or so, the time is slightly longer. Some of the basic laws of robotics which were actually introduced in 1942 by Isaac Asimov is a robot may not injure a human being through inaction or allow a human being to come to harm. Rule number 2, a robot must obey the orders of a human being except where it conflicts with the first law. And then third, the robot must protect its own existence as long as that protection does not interfere with law 1 and 2. So these are the basic laws of robotics, but more important so, we have to keep in mind that we're working with a machine, and the machine is programmed, and operator safety is a main concern. So when we are working in a lab, we must make sure that we do not come near the robot while it is in operation. We don't want to stick hands or head to get a close look or check anything when the robot is in operation. Do not stick fingers into the mechanism, or they may be caught in between the gears and belts. Do not make any connections to input, output, or any other connections of power or a motor when the switch is set on, and do not remove the controller cover while the controller is plugged into the 110 or 220 volts AC. Mostly we have to use common sense and keep off the machine while it's working. When we do motion with the robot, this is the robot we'll be using in a lab, then we have some other safety rules. When we move long distance, we will move only at 50% of maximum velocity. When we come to an approach position before we pick up a part, then we'll move at 10% of maximum velocity. If we have an obstacle, then we will use a circular approach in order to avoid interference with these obstacles. We have to keep in mind that when we move long distance, the gripper should be closed, such it takes less space and has less of a chance to collide with other objects. A point where we connect at the tip of the robot a tool to the robot is called tool center point, and this is the point where we mount the tool or the part to the system. If this is a gripper, it will be mounted over here, but we may have some offset that we may have to define towards the center of that tool or part, and that is the offset that has to be programmed into the system. You see over here we have a SWAT welding gun, so the tool center point is right in here. We see over here we have a brazing gun, so this is the tool center point. We have over here an example of a gripper, and that is the tool center point of that part. The payload that the robot can take is the maximum mass that it can carry while maintaining specific accuracy and load carrying capacity. And over here we see the work envelope of the system. This is a planar view or top view that we see that the robot tool center point can reach all of these areas over here, which are bounded between these two lines. And also on a cross-sectional view, you see some odd shape, and we will learn how to calculate these work envelope of various types of robots. So this is the surface of revolution that we have to revolve so many degrees over here in order to get the area or the space where the robot may work. And you see that there will be some vacancy over here which the robot will not be able to reach, and also in the back there is a truncated segment that the robot will not be able to reach. The robot, as we mentioned earlier, has links, and the links are connected with joints, and the joints are of two basic types. One are called Revolutes, these are rotary joints, and one are called prismatic, which are sliding joints. An example of a Revolute joint is a ball bearing, as we see over here, and an example of a linear or prismatic joint is a sliding bushing. The prismatic is defined as P, and the Revolute is defined as R. Now the robot has degrees of freedom. Each one of these joints presents 1 degree of freedom. In order to position any part in space, we need minimum 6 degrees of freedom. If we have 7, then 1 is redundant. Sometimes it's being used to avoid obstacles, but typically 6 degrees of freedom, 3 linear, X, Y, Z, and 3 rotary, pitch, yaw, and roll. The degrees of freedom should be designed to have low friction for smooth motion and high repeatability. They also should have high stiffness. High stiffness results in high natural frequency, which also implies high servo bandwidth. High servo bandwidth means that the servo system of the motion controller and the servo amplifier and the entire load could respond quickly to changing environments. And typically we like to have high servo bandwidth to any automation machine. Load capacity should be high enough of the joints and the links to provide the specified life for the robot as a whole, is made of the sum of the life of its links. Okay, the life of the robot will not be longer than the shorter life of one of its link. Here's an example of a prismatic linear joint, which is recirculating linear bearing, and here is a typical Revolute joint included within the portion which is connected to the link. We may have a link over here of a robot and another link over here, and the two links will be connected with the Revolute joint. The robot links are required to move in some type of motion profile, which is programmed within the robot motion controller, and a typical motion, and again this depends on the dynamic stiffness, how stiff is the robot when it is moving in high acceleration. If it's not as stiff, you will see there will be an overshoot and also oscillation. And this is a settling time, and we define the cycle time as the time for a back and forth motion, and then the move time is the time that it takes for the robot to start its motion, excel, and then complete its motion over here with the decel, and this is the settling time. A dwell in between the forward and backward motion is also very important, to cool off the motors and make sure that the robot meets with each one of its link its specified specification for the motors. Here we see 3 degrees of freedom. We have X, Y, Z of the robot, which will position this point over here anywhere in an XYZ space, and it can be done with a combination of Revolute and prismatic joints. We see over here we have one Revolute for the yaw, we have another Revolute for the pitch. This link will go up and down, and we have another prismatic for the in and out. The 3 of them will provide XYZ, and then over here we have pitch, yaw, and roll, another 3 degrees of freedom, a total of 6 degrees of freedom to position the tool center point anywhere in space in any orientation. We will talk more about accuracy, repeatability, and resolution in upcoming system. Right now we'll just take a look. This is a robot that we will be using in a lab. It has some definitions of its different links. This is called the elbow. This is called the wrist. This link is called the shoulder. And over here, this is the base. Each one of them has a micro switch for a limit, to limit its position. And over here we have a gripper. Each one of these joints is operated with a motor, and also the gripper is an electric gripper, which is operated with a motor. The type of robots that we will be investigating are, as shown over here, the SCAR robot has Revolute, and prismatic. We see over here that this Revolute provides the yaw. This Revolutes provide a secondary yaw, and this prismatic provides an up and down motion. So we call that RRP, and that is the SCAR robot. Very common in assembly work. Seiko, many years ago, surprised the world how they can make very high reliability watches. And the secret was that they were using SCAR robot in the assembly process. Over here we see a robot which is spherical. You see that it includes a Revolute for the yaw. It includes a Revolute for the pitch, and in and out prismatic for the third degree of freedom, and that will position this point anywhere in XYZ space. Of course, there may be another 3 degrees of freedom over here for the pitch yaw roll of the wrist. It's called spherical because you see that this pitch, the tip, can actually generate a sphere which will be truncated at the base, and it will be hollow because the robot will not be able to reach a distance where this point over here is coming down to this point over here. The robot will not be able to reach here. So in order to calculate the work envelope, we will need to calculate the sphere of this maximum radius, and it will be truncated by the floor, and then it will be hollowed by another truncated sphere, which is defined by this radius vector. We'll do some exercises with this coming up. This is a cylindrical robot. It has Revolute for the yaw. It has prismatic for the Z, and in and out another prismatic. And you see that this point can actually scribe around a circle, and coming in, it's going to be a hollow circle. It cannot go less than the length of this link because it's fixed, and then it will go up and down as much as the prismatic link will allow it. And therefore the work envelope will be a cylindrical, hollow cylinder. This will be the inner radius, this will be the outer radius when it is fully extended, and the height of the cylinder will be the travel that the prismatic can go up and down. So this is called RPP type of robot. This is perhaps the most common robot out there, which is called articulated robot. It's RRR. It has Revolute for the yaw, Revolute for the pitch, and then it has another Revolute for a secondary pitch, and then we'll put this point over here before the pitch yaw and roll of the wrist in XYZ position. So you see a complete robot will have 6 axes, axis 1, 2, and 3 is shown over here, and then the 3 rotational. These robots are extremely common in industry, together with the last robot that we have over here on a common one, which is called the Cartesian robot. This is P, and P, prismatic, prismatic, prismatic in XYZ, and you see that the work envelope of this robot is simply a box which is including the space where that tip over here can move. This can go up and down. So this will be the height of the box. This will be the width of the box, the travel over here, and this will be the length of the box. And this Cartesian robot can have game tree configuration with 2 axes for the X, and it can also have XYZ, very typical configuration. We will look later at the differences, but for now, these particular robots are extremely stiff and considered a very high performance. They can fly at extremely high speed, like 3, 4, 5 meters a second, and obtain accuracy which is on the order of microns, while the articulating robot can fly very high speed, but the accuracy is limited. The stiffness is much lower, about 10 times lower than the Cartesian robot. They are being used for applications like painting, glue dispensing, and pick and place, brazing, spot welding, and these guys are being used for semiconductors and electronic and assembly equipment where precision is extremely important. There are other types of robot which are called the tripod. This is prismatic by Festa Corporation. I suggest you click on that YouTube and you see how it works. Extremely fast device. And here's another one that has actually Revolute, to actually do the same thing as a tripod, but it is working instead of a prismatic joint with Revolute joints extremely fast, and it's being used together with vision for high pick and place of parts from conveyors. We see here an example of a robot by Kiva, used extensively by Amazon, and it has in fact wheels, and it is navigated autonomously within the factory and has a Z-axis that can lift the whole container with parts and bring it in with the wheels to the fulfillment center operator. The Scobot robot that we'll be using is a type RRR, or articulating, and we already saw that it has base, shoulder, elbow, it has pitch, roll, and also has a gripper. So it's only 5 degrees of freedom with a gripper, being able to also measure parts as it opens and closes. A typical construction of a robot has a frame, it has a base, it has a manipulator of each one of these links. It has an actuator. Sometimes it could be a cylinder that makes the system move, or it could be a gear or belt. It has links, as we see over here. It has joints which connect the link, and it has a gripper. On the electrical side, it has motors. It could be stepper, servo, torque, or linear, encoders of various types, limit switches, visions, camera, servo amplifier, motion controller, PLC, power supply, and miscellaneous equipment like cable carriers, teaching pendant, and cabinet. The robot position system specification that are many times of concern related to kinematics, including acceleration, velocity, displacement, work envelope, degrees of freedom, dynamics such as mass, load capacity, and inertia. The position and accuracy, repeatability, and resolution, we'll talk about them in a special lecture. We'll talk about the dynamic accuracy, including smoothness of motion, settling time, overshoot, following error. Several filters we'll talk when we discuss motion controllers of robot, specifically the proportional, integral, and derivative filters, the PID. We'll see how they're related to position bandwidths with the stability criteria, including phase margin and gain margin. And then power is always important to assure that the robot can do its job, including force and strength, stiffness, natural frequency, modes of vibration, and then the environment that the robot is working in, such as humidity, cleanliness, shock and vibration, thermal, magnetic, and electromagnetic interference or radio frequency interference. These are the specifications that the robot manufacturer will provide the user in order to design the process. The typical performance analysis and testing areas are repeatability and accuracy, modal analysis, constant velocity, settling time. These are testing which are being done on robots, time and motion studies, workspace envelope, inverse kinematic workspace envelope calculations. We will do some of them in our laboratories and also in the exercises. We'll calculate the inertial loads. We'll also look at robot strength, which relate stiffness and force and deflection. We do life estimation, and very important are the reliability, the mean time between failure of the robot, which is going to affect the return on investment, the controls and the cost, the life cycle cost, the return on investment. We'll spend time on that, and then also component sizing of motors, encoders, actuators, and grippers. Now, the last thing I'd like to mention in this discussion is an epilogue about the relationship between testing and system analysis. Based on my many years of experience, a test is a small value unless you can learn, conclude from it about the behavior of the tested system. The behavior of the system is the interrelationship between the performance and various parameters and environmental conditions, and it is described as a mathematical models which relate the variables and parameters of the system, and it does not have to be complex. It could be very simple, yet allow us to learn about the behavior of the system we're dealing with. An experiment is extremely important to validate the mathematical model and then apply the model into a more complex situation that are a little bit more difficult to visualize. We can use Excel, Inventor, MATLAB, MathCAD, Lisa in order to do these analysis. In our case, we will be using mostly Excel, and we'll use a little bit of MathCAD and MATLAB. If a test result agrees with the predicted results, this is a good indication that we understand the system and we can go forward and get into detailed design and then into manufacturing. If there is a disagreement between the test results and the model result, then it means that either one of them is probably in error, and we have to go through a troubleshooting process as needed in order to figure out what's wrong and resolve it. This concludes this presentation, and we will continue with upcoming lectures. Thank you.